In this video, we'll be exploring powers and exponents. Powers and exponents come into many applications in real life and careers. For example, how bacteria populations grow, or how the amount of medication decreases once absorbed in the body. Almost every branch of science and even economics makes use of exponents. To explore powers and exponents, let's explore an interesting problem, which involves figuring out how many red triangles there are in this pattern. This pattern is known as a Sierpinski triangle. Before we explore this further, see if you can come up with a strategy to determine how many red triangles you see. The Sierpinski triangle is an example of a fractal. A fractal is a never-ending pattern in which each part has the same structure as the whole. To illustrate, notice the whole has these three equilateral triangles. And we see this same pattern in each smaller section. Let's look at the pattern of the whole and call this stage 1. Later stages apply the same pattern to each part. Our problem was to figure out how many red triangles are in this stage. So let's return to stage 1 and see how this pattern grows. Stage 1 has 3 triangles. In stage 2, we can see those 3 triangles, but now there are 2 more groups of them. In total, we now have 3 groups of 3, which is 9. In a similar way, we see stage 3 has the 3 groups of 3 and 3 groups of those for a total of 27. Now we're back at stage 4 and see the 27 triangles, and then 3 groups of those. Our total number is 81. Our answer to the problem can be found by multiplying 3 by itself 4 times. We can represent this repeated multiplication using what is called exponential form. The 3 represents the base, and the 4 represents what's called an exponent. When a number, the base, is raised to an exponent, it is called a power. For example, this power, which we recite as 2 to the power of 5, means the same as 2 multiplied by itself 5 times, which evaluates to 32. Here are a couple of examples for you to think about now. Write each in exponential form, then evaluate. The first one means negative 2 multiplied by itself 3 times, which equals negative 8. The second one means 3/4 multiplied by itself 4 times, which is 243 over 1024. Let's apply what we've learned about powers to the Sierpinski triangle pattern. Stage 1 has 3 to the power of 1, which is 3 red triangles. Stage 2 has 3 to the power of 2 red triangles, which is 9. Continuing this pattern, we see that stage 4 has 3 to the power of 4 red triangles, which is 81. Now that we have a way to describe the pattern numerically, we can extend the pattern to stage 5 and stage 6, and we could keep going. But for now, let's apply what we have learned about powers and exponents to some sample questions from the textbook. In a children's story, Double Dan the Dragonfly is growing fast. His body length doubles every month. At the beginning of this story, his length is 1 centimeter. After how many months is his body length more than 50 centimeters? Let's first identify the key information given to us in this problem. We are told that his body length doubles every month and that he begins with a body length of 1 centimeter. We are asked to figure out how many months it will be until his body length is more than 50 centimeters. One way we can solve this problem is to organize our information into a table. In the beginning, 0 months have passed and his length is 1 centimeter. After 1 month, his body length has doubled once, which we can write as 2 to the power of 1. After 2 months, his length is 2 to the power of 2, which is 4. Continuing this pattern, we see that it takes 6 months for his body length to be more than 50 centimeters. In this next problem, we are asked to evaluate each expression. Take a moment now to think about how you would evaluate each expression. To solve problems like these, we need to use what is called the order of operations. Order of operations means there is a specific order in which we must do the various operations. First, we evaluate what's inside the brackets, which we see in the second problem around the 6 minus 2. The numerator and the denominator of a fraction can also be considered as within brackets, so we need to evaluate each of those before we evaluate the fraction as a whole. Next come the exponents, which we see in various places in our problem. Next is to divide or multiply in order from left to right. In the left problem, we notice that the 2 is multiplied by 3 to the power of 2. Finally, we add or subtract in order from left to right. There are several such operations in these problems. You may be familiar with BEDMAS as an acronym to remember the order of operations. Let's now apply BEDMAS to these problems. In problem A, we first need to evaluate the exponent, and 3 to the power of 2 is 9. Next we need to multiply, and 2 times 9 is 18. Finally, we need to subtract, and 7 minus 18 is negative 11. In problem B, we first need to evaluate what's inside the brackets, and 6 minus 2 equals 4. Next, we need to evaluate 3 powers which have exponents. Negative 3 squared is positive 9, 4 squared is 16, and negative 4 squared is also 16. Next, we need to add and subtract, and this leaves us with negative 7 divided by 0. Unfortunately, after all of this work, we can't divide by 0, so our answer is described as undefined. Related to working with powers and exponents are what are called the exponent laws. These laws come into action when we operate between two powers. For example, when we multiply powers, divide, or raise a power to a power. Let's first look at multiplying powers. 3 squared is 3 times 3, and 3 to the power of 4 is 3 times 3 times 3 times 3. Bringing this together reveals that we end up with 3 to the power of 6. Observe the exponents. What relationship between them do you notice? You may have noticed and reasoned that the sum of 2 and 4 gives us the 6. So to evaluate when we are multiplying powers, we need to add the exponents. We can generalize this law as a to the power of m times a to the power of n equals a to the power of the sum of m and n. Next, let's think about what happens when we divide powers. When we multiplied powers, we added the exponents, so what do you think we might do this time when we divide powers? Three to the power of 5 is 3 multiplied by itself 5 times. And 3 squared is 3 times 3. When we bring these together, notice that there is a common product in the numerator and denominator. Anything divided by the same thing is equal to 1. Multiplying by 1 does not change the product, so we are left with 3 times 3 times 3, which is 3 to the power of 3. Once again, notice the exponents. We can see that this time we can subtract the exponents to get the 3. So when dividing powers, we subtract the exponents. We can generalize this law as a to the power of m divided by a to the power of n equals a to the power of m minus n. There are a couple of other things to note about this law. First, we need to state that it is only true as long as a does not equal 0. This is because we cannot divide by 0. The second is that we can use this law to bring meaning to having 0 as an exponent. We can replace the 0 with m minus m because that equals 0. This exponent law says that this is the same as a to the m divided by itself. But as we saw earlier, anything divided by itself is equal to 1. So anything to the power of 0 is equal to 1. Once again, we have to state that this is only true as long as a does not equal 0. Finally, let's explore what happens when we raise a power to a power. 3 squared to the power of 4 means 3 squared multiplied by itself 4 times. But when we multiply powers, our first exponent law states that we should add the exponents. So this equals 3 to the power of 8. Notice that we have 4 groups of 2, so what we are doing is multiplying the exponents. So when we raise a power to a power, we multiply the exponents. We can generalize this law as a to the power of m to the power of n equals a to the power of n times m, which we usually write as a to the power of mn. In summary, we learned that when multiplying powers, we add exponents. When dividing powers, we subtract exponents. From this we learned why anything to the power of 0 is 1. Finally, when we raise a power to a power, we multiply the exponents. Two other relationships that can come into play are that if we take a power of a product or quotient, the exponent applies to both terms. Let's apply what we have learned about the exponent laws to answer some sample questions from the textbook. We are asked to express each of these using a single power, which means expressing each with one base and one exponent. How do you think we can use the exponent laws to answer these questions? For problem A, the first term is a power of a power, so we need to multiply the exponents. Now we are multiplying powers, so we need to add the exponents. The answer is 3 to the power of 11. In problem B, in the numerator we are multiplying powers, so we need to add the exponents. Next we are dividing powers, so we need to subtract the exponents. The answer is -4 to the power of 3. There are several situations in which students make common mistakes in this unit. First, let us consider -4 squared. Many students interpret this as -4 times -4, which would be positive 16, but this is not correct. Instead, we need to recognize that with order of operations, the exponent must be evaluated before the negative, because the negative is equivalent to multiplying the power by -1. So we actually get -1 times +16, which is -16. Another mistake can occur when multiplying powers with different bases. Some students multiply the bases together and then they think they should add the exponents. But 6 to the power of 5 is not the correct answer. The exponent laws only apply when we have powers with the same base, so we need to evaluate these powers separately and then multiply. This gives us -8 times +9, which is -72. With a context problem like this one, students need to interpret the words and model them mathematically. A student may correctly recognize that 200 bacteria doubling should be expressed as 200 times 2, but then incorrectly look at the length of time and not notice the units. The bacteria double every 20 minutes, which is 3 times per hour. So we need to realize that 4 hours represents 4 times 3 doublings, so our exponent should be 12. Another mistake some students make is to multiply the 200 by 2, and then raising 400 to the power of 12. But the order of operation tells us that we need to evaluate the exponent first. So the answer to this problem is actually 819,200. This video addresses several learning standards in the Mathematics 9 curriculum. In content, we looked at exponents and exponent laws with whole number exponents. Several curricular competencies may emerge as your child learns and applies the content from this chapter. Our primary focus this video was to use reasoning and logic to explore, analyze, and apply mathematical ideas. We did this when we developed the exponent laws by noticing the relationships between the exponents.